Okay, good morning. Yeah, so this is Monday. Yeah, I record this one in the morning of Monday morning. Okay, so this is the last tutorial. Basically, we are given called directed acyclic graph, DAG. They are like this. Yeah, so you should not see a loop. Yeah, although you look at it, maybe the one like that, you can go to 7, but 7 cannot go to 6, all right? And 6 go to 5. Yeah, this one will not form a loop. Yeah. The others also you can try it. Yeah, it will not form a loop. So this is the feature of this DAG. Yeah. So in figure 1, we want to know the topological sort of this graph here. So to solve this problem, first of all, we create a table like this. So we have the node, the size of that, yeah, the array here will be like that from 1 to 10 because there are 10 vertices here. For each one of them, we have to find the in degree. So in other tutorials, I think we have introduced the in degree and out degree. In degree is to go into that particular node. So you look at 1 here, you cannot go there. So the in degree is 0. So how about 2? 2, you can go from node 1 to node 2 and node 3 to node 2. So the number of in degree is 2. So the other one, we pick another one, 7. Yeah, 7 is like this. You can go there from 6. You can go there from 5. That's all. Yeah, so 7 is also 2. So the others, you can do it accordingly. Okay, so basically it's just like you take subjects. Yeah, you took subjects in NTU, something like this. Yeah, so this course has no prerequisite. Yeah, so 2 you need to take maybe 1 first, and then take 3. Both of them you fulfill the requirements, then you can take the course number 2 and so on. So you can view it like that. Yeah. Okay. So how do we do it? This topological sort here. Now, so you check the in degree for all the nodes here. This one is 0. 1 is 0. So what does it mean? It means no prerequisite. Then you can take this one without any pre-requirements. Yeah. So we take it. So 1 will be the 1 here. Yeah. Now, once we take the 1, we fulfill the requirement, then the requirement for 4 will be reduced by 1 because the in degree will be reduced. Similarly, for 2, you don't need to include 1 because you have fulfilled the requirement. So the in degree of 2 will be affected and 3 will be affected. Yeah, so will be reduced by 1. So all the in degree of this 4, 2, 3 will be reduced by 1 because you have fulfilled the requirement. So the number of requirement for individual one will be smaller. Okay, so you see that here 1, 3, and 4, each one of them will be reduced by 1, the in degree. So now they are 1, 0, and 3 respectively. So looking at this one, what will be the new subject that we can take without any prerequisite? Yeah, we have fulfilled all the requirements. So you look at the array here, number 3 is 0. That means we fulfill all the requirements and we can take this course now. So in this case here, 3 will be the next one we can take. So from 1, then we should take 3 without any problem. So you look at it, for 3, you can fulfill, if you have taken this one, 2 will be reduced by 1, yeah, so no more prerequisite from 3, and 6 will be reduced by 1, yeah, so the node 3, the in degree, right? So next, when I advance to one more level, then 2 here becomes 0, and 6 also become 1, 2 minus 1, and so on. So accordingly, you see that 2 and 6 will be reduced by 1 respectively. So accordingly, this is 0. Once it's 0, that means we can take it out, and 2 will be the next one we take. And 1 here, yeah, so this one from 6, the corresponding in degree will be reduced by 1. Now it's 1, right? So we keep on doing that. Yeah, so the next one we take is 2. So we need to take 2. So 2 is here. Now, once we take 2, you can see that it will affect the 4, the in degree of 4. It will affect the in degree of 6, and so on. 4 and 6 will be affected. So later on, you will see that 4 here will be reduced by 1, become 2. This one becomes 2, and this one becomes 0, right? 1, you minus 1 becomes 0, and so on. Okay, so as what we expected, this one becomes 2, this one becomes 0. Since 0 has no prerequisite now, then we can take 6. Yeah, so this is the, the way we do it. Okay, so once we go to 6, we can go to 5, we can go to 7. So both of them can be reduced. Okay, so 5 becomes 0, 7 become 1. Since this one we fulfill all the requirements, then 5 will be the next one, will be the next one we take or we visit. Okay, so 5. So go to 5. 5 will affect 4, will affect 7, and that's all. So 4 and 7 will be affected. Okay, so for the in degree becomes 1, 7. For node 7, the in degree becomes 0. So we fulfill all the requirements of node 7. So node 7 will be our next one to visit here. So those underlined we have visited before. Okay, so 7. 7, you look at it, you can go to 4, you can go to 9, you can go to 8. So all these 3 nodes, the in degrees of them will be reduced. Okay, so 4 becomes 0, 8 becomes 0, and 1, this one 9 becomes 1 here. So this one 4 and 8, actually you can write 8 and then 4, no problem, because both of them are okay. So you can put 8 first and then 4, but here we'll make it nicer, right? Yeah, 4 and then 8, yeah. But remember that it should be very flexible. Okay, so now we go to visit 4. Now visit 4, as you can see that there's no in degree. So the in degree is 0 now. But once we do it, we cannot go to anywhere. We will not affect any others. As you can see that you cannot go to anyone affect others. So we visit it, but we don't get any new note here. Okay, so we visit it and 4. That's all, because it cannot go anywhere. So the next one is 8. 8. One is 8 here. You see that 8 will affect 9, will affect 10, and that's all. So 9 and 10, each one of them, the in degree will be reduced by 1. Okay, let's try it. Yes, this one becomes 0, this one becomes 1. 9 will be added to this topological sort, the list here. So we visit 9. Once we visit 9, then the requirement for 10 can be reduced by 1. So this one will be reduced by 1, and this one will be add to that, and then we visit it. Yeah, so you see that this will be the last one we visit, and we have visit all the vertices here. So if you take the courses like that or you visit like that, you don't have any problem to fulfill the prerequisite issues. Yeah. Okay, so I think this one is quite easy to see lah. Now we go to the next one. Now, when we go to the next one, we are given a graph here. So the spanning tree of the graph shown here by using the Cusco's algo. Yeah, Cusco's algo is like that. Yeah, Cusco. We want to form the MST here. So that means we have to include, visit all the nodes here, and the corresponding rate, the total rate for all the branches or all the edges should be minimum. So the Cusco's algo is like that. First, we look at the rate here, which is the minimum because we are using the greedy strategy here. So you see that this is 1 cheaper, right? In some way lah. So this is 1. So this is 1, and I can see 3 of them lah. 1. This is 1. This is 1. This is 1. So you will take in all these 3 branches here. Okay. So okay, so the key principle of this Cusco, I think this one is K, K-A-L. So this is should be K-A-L. I have no time to change it. So I think you know what I mean. Okay, so it's like that. Select the minimum weight edges without cycle. So you always select the minimum weight edges, and then you cannot form cycles. Yeah. So this one, yes. This one, yes. This one, yes. So in this way here, we will visit. We will take these 3 branches. So this one is 1. This one is 1, and this one is 1. So the corresponding edges are listed here. Okay, so once we take in the minimum 1, so now what are the other minimum edges here? So this is 1, this is 1, 1. The next one smaller is 2, right? So this one will be, we'll take this one. We can also take this one. We can also take this one. I can see 3 of them. Yeah, you see more, then you should include them lah. 3 of them. So once we take this one, we have to notice that whether they will form cycles here. So this one will not, this one will not, this one also will not. So we take in all of them. So the next step is to take in this minimum weight edges, minimum weight edges. So 1, 2, and 3. We take in this one here. The blue one are the old one. We have taken already. So the next one you will be 3, all right? Yeah, because 1 and 2 we have taken. So 3, but you don't see any 3, right? So cannot see any 3. Cannot. So the one after that should be 4. So this one is 4. This one is 4. This one is 4. This one is 4, and so on. 1, 2, 3. They don't form a cycle, so we can take them. So This one also can. This one also can. So 5 of them, they don't form cycles here. So as you can see that, so each one of them, you have to check whether you will form cycles here. If you don't form, then that's all. Okay, no problem. You can include that. So the next one is 5. So we have seen 5 here. We have seen 5 here. So okay lah, huh? 5 here. So 2 of them, I can only see 2 of them. So this one, will you form a cycle? No, will not form a cycle. And this 5 here will not form a cycle. So both of them are okay. So these 2 are okay. Now we go to 6, right? 5, and then the next one, smallest one, is 6. Okay. Which one is 6? Okay, let's look at it here. Can you include this one? The answer is no, because once you include this one becomes a box, right? A square or a box is a cycle. Yeah, so this one cannot be included. This one here, okay, right? This one here from 11 to 14, also okay, this one. And so this one we should include. So if we say we include this one here, okay lah, so we will not form a cycle. But once we include this one, we cannot include that one, because once you include it, you can see that they will form cycles, right? They will form cycles, yeah, like that. So these two edges here, we can select one of them. You can select this one or you can select this one, but you cannot select both of them. Otherwise, we will form cycles, and this is not allowed. So I select this one, I select this one. So I don't select this one, because once I select this one, we'll form a cycle. Once we select this one, we will also form a cycle. There's a choice here. Yeah, you can choose this one, but not this one. I think I have explained for you. Then now you look at it. You have connect all the nodes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. Yeah, you have connect them. And this one will be a tree, right? Spanning tree. Yeah. And because you don't have cycles. Yeah. And also should be minimum, because every time you select the edges, they should have the minimum weight at that particular time. Yeah. So this is the way how we do it. Okay. I need to check with some students. Some students join this section. Yeah, I'm not going to open that. Later on, I will send them the link. Okay. Okay, so I finished question number 2. Now we go to question number 3. So this one is all the path we include here, altogether 16 of them. Okay, next one. The next one is like this. Consider a rated graph here. So the rated graph is here. You have four vertices: S, A, D, and B. Okay, so those are the nodes here, four nodes here, very simple. And the rate for this one is 1/2, this one is 1/8, this is 1/2, this one is 1/16, this is 1/8, and so on. Okay, so I think I have explained that. This is the rate here. So suppose all edge weights are between 0 and 1, as you can see that, because it's 1/2, 1/2, 1/8, 1/16, 1/4, and so on. We assume that they are between 0 and 1. And we are going to start from S. This one is S. This one is S, right? And then we would like to go to D. We would like to go to D. So we have to see what's the path to do it. Yeah, say, and the requirement is the product of all these weights here should be the maximum. Say, for example, from S to D, we choose this path here from S to A, from A to D. This one will be 1/2, this one will be 1/16. So you multiply them together is 1/32. So this one here is 1/32. If you choose another one from S to B and then to D, this one will be 1/8 times 1/4. So it's 1/32. Like that. So there are many possible ways to do it. Say, for example, if you can do it like that, you can go to A and then go to B and then go to D. There's another path here. So we should examine all these possibilities here using the some method here, such that the product should be maximum. So here we would like to find an efficient way to do this and trace the steps for the graph shown in figure 3. This is figure 3. To show this one here, as you can see that the product is maximum. Individual one, you multiply them together should be maximum. And individual weight here is 1 between 0 and 1. So you should link something to what you have learned here, because you have learned the minimum path, minimum weight path. So you should try to transform this one to minimum path problem, transform it, then you can apply the minimum weight path method. Shortest path method to solve the problem. Okay, so as you can see, this is product, and the one we know is the sum of them, right? Yeah, because minimum weight, right? So you have to transform this one from product to sum. So as you can see that, how can you transform the product to sum? You have to take the log lah. And log is good, you see, because once you take the log, then this one will be, you log the weight plus the log of this weight plus and so on. So fulfill somehow the requirement, but still some problem here. If you take the log here using base 2, this one become -1. This one -4, and this one -1, and so on. So you have the minus here. How can you sum them together and try to manipulate it? So you should get rid of this minus here. So you have to transform this one to 1. Take the exponent 1 without the sign. This one you should transform it to 4 without the 1 here, because you want to maximum this one. Yeah, so this one becomes very small individually, all right? So 2 to the power minus 4. So you want this one, that means in our new, when you transform this one, it should be very big. We should not choose this one. So this one, you have to take out the minus sign, becomes 4. This one becomes 1 and so on. So with this explanation, I think now is quite possible to look at it. You have to take the log, and then you don't want the minus sign. You get rid of the minus sign. So we will transform it in this particular direction. Okay, so no need to read this one here. Now, so previously we have 4 nodes, we still have 4 nodes here, as you can see that. But now when we take the log, this one should be minus 1. We don't take the log, we take the log, but we want to get rid of the minus sign. So when you take the log, you should take 1 over something. Yeah. So in this case here, the 1 over 2 become 1. And this 1 over 16 becomes 4, and this one becomes 3, this one becomes 2, and this one is 1, and so on. So now, as you can see that once we do this simple transformation here, 1 over the rate of that, and take the log. The base is 2 so this one, the base is 2 here. So you can see that we'll transform the original graph in this particular manner. So we can use the Dijkstra's algorithm to solve this problem. Try to find the shortest path from S to D. Yeah, because we have to transform this one, we would like to find something shortest path. Okay, so we would like to maximize this one is equivalent to minimize that particular one here. So you see that we can transform it to like that. Once we transform that, we can use the Dijkstra's algorithm, to find the shortest path. Yeah. Okay. Give me a minute. Yeah, I want to tell them, because some students are waiting for that. I think they don't read it. They don't read the check. Yeah. I think I have explained already. Okay, so go back to here. Now we are going to see how to use the shortest path to do it. Now, shortest path is like that. Yeah, you use the Dijkstra's algorithm. So first of all, you have the starting point. The starting point is S. S, right? So you can go to A. So you remember that you can go to A, and also you can go to B. Both of them are possible, but you want to find the minimum, right? So you can imagine that this one is $1. You use $1 to go to A, right? And you use $3 to go to B. There are only 2 possibilities here. So which one you go? Of course, you see in front of you, one you have to pay $3. The other one you have to pay $1. You will choose the one cheapest. Yeah. So 1 is the one you choose. So you will choose this one from S to A first. Okay, so I think on the next page, I will have the graph to explain this idea. Okay, so first of all, from S to A, we have to pay $1. From S to B, we have to pay $3. So then we will try to find the minimum. The minimum is here. So we will take this one here. We'll take this one here. So now this group here consisting of two nodes, S and A. S and A. Don't think that you must be here. No, yeah. So now based on this one, this is group here, they try to expand their territories here. So you see that from this group here, they can go to B. Now, once they can go to B, they have to pay $3. But if you go to A, you go to B, is $1 and $1 here. So it's 2. So by simple comparison, you see that this one is cheaper. So that's why we label this B not by 3, is 1 plus 1. So it's $2. And from A, because you see that this is a group, from this group here, you can also go to D. If you go to D, how to do it? You spend $1 to D, and then you spend $4 to D. So totally, you have to pay $5. So now, as you can see that, now you are in this group, you want to expand your territory. If you include B, you have to pay $2 because from S to B is $2, right? From S to D, in this particular path here, because you go to A and then go to D, you also need to pay that. It's even higher, $5. So $2 and $5. Which one you select? You will select the cheapest one, which is 2. So in this case here, you will include this one into your group. So from A to B. So in this way here, this group here, you have 3 members, 3 nodes, S, A, and B. You select that particular path. Now you want to expand. So you have to check it. How do you go to D? You can go to D is from A to go to D, which is 5, right? Because you have to pay $1 to go to A, another $1 to go to $4 to go to D. So totally is $5. Yeah. So if you do it from 2, S go to A and then go to B and then go to D. In this case, it's $1, so it's $2 lah. Now you add another $2 here, so this one becomes $4. This one becomes $4. So if you choose the S to A, from A to D is $5. If you choose from S to A and then go to B and then go to D, you have to pay $4. So $4 will be cheaper. So you will put 4 there lah. Okay, so lastly, we will have to choose this particular path here. So you can see that from B to D. So this is the answer. We have arrived at the destination, which is D lah. So from S, you can go to D by using this path, and you need $4 to do it. And this is the cheapest one here. Okay, so this is the answer for question number 3. So when you do this problem, always say that you are one member at the very beginning. Now you connect to A, then this one becomes a group. From this group, how can you expand it? You can go to B and D. So you look at it, which one is the cheapest to go to B, which one is the cheapest to go to D, and compare these two values here. And the smaller one you will choose. So that's why we will include this one as a new member, right? So we'll choose this path lah. So from here, so for this one here, how can you go to D? You may have a few ways to go to D. You choose the cheapest way to do it, and then that will be your final answer. Okay, Okay, so this is I put a remark for the chat here because some students are trying to join this class here. Okay, here is like this, yeah. Okay, let me explain this one here. So you have a graph here. This one is G is a graph, and from the graph, you can form the tree, right? You can form the tree, the minimum spanning tree here. So here is suppose that the weight of the edges incident on V are distinct. So that means this is V, this particular V. There are many edges go to V. From W go to V, from W pi go to V, from here go to V, from this one go to V, from this one go to V. Now out of this, at least 6, one here, this one is the minimum. The E is the minimum. Let E be the edge of minimum weight incident on V. So that means you can go from any direction to go there. But you look at it, which branch is the above minimum weight, you find that E is there. So we would like to show that E is contained in every minimum spanning tree. So that means if we form the minimum spanning tree, you must include this E here. You cannot include others. So that is the we want to prove. So how do we do it? Here we will do it by contradiction. So we assume that based on this graph G, we can form a tree, minimum spanning tree, and we don't include E here because by contradiction. So we don't include E, we include E pi. Another one, say for example, because there are 6 of them, right? From here, you can see that 6 of them. We can assume that in this minimum spanning tree, we include another one called E pi instead of using that. So our argument is like this, yeah, because it is a minimum spanning tree. If you remove this one, they will be broken into 2 pieces here. But if now we add the E to it, this particular one here, and these 2 components will be drawn together. And you compare the total weight for this spanning tree here. So this one is all the other weight plus E pi. This one is all the other weight plus E here. So since E is smaller than E pi, so the total weight of this one cannot be smaller than that. So that means this is not a minimum spanning tree. This is not a spanning tree because this one is cheaper, minimum spanning tree, right? This one, the total will be smaller than that. So this one cannot be minimum spanning tree. So it's a contradiction. So at the very beginning, we make the assumption that this is a MST, which is wrong. So that means if we don't include the E here, cannot be a spanning tree, cannot be a minimum spanning tree. Now, suppose that this one is not contained in the minimum spanning tree, just like that. Then so you argue that this E pi, the weight of that is this one is bigger than this one because we have to make the assumption already. There are so many edges incident on that, and E should be the minimum. So now we removed this one. We remove this one and add back another one to join them together. So you can see that this one will have the total weight smaller than that. So this guy, this spanning tree cannot be the minimum spanning tree. So we have proved that this is not and impossible if you don't include it. So the contradiction, is very often we use it. We assume that this is a minimum spanning tree, and later on we somehow we find the problem and then verify that this cannot be a minimum spanning tree. So that means you must include that. Okay, so this one is Q4. So another way to do it. So when you draw this graph here, no need to be so complicated. Maybe use something simple to illustrate the idea we'll do lah. Okay, so now we move on to the next one. The next one is related to what we call the one-hop and two-hop adjacency list here. So hop means you one step. So one step you can go to, say from 1 you can go to 2, you can go to 3. So I make it simple. We say that from 1 you can go to 2, from 1 you can go to 3 lah. From 2 you can go to 1. So as you can see that from 3 you can go to 1, you can go to 4 in one step. So one hop adjacency list, 4 of them, right? 4 you can go to 3 and so on. So this is one step. So in the problem for Q5, we are given this one hop adjacency list. This particular adjacency list, one hop. We would like to form the two hop. Two hop is like that. You walk 2 steps. Say from 1, you can go to 3, then you can go to 4. So you can go to here, go to 4. All right. Now you cannot say that from 1 you can go to 3, you go back to 1. This is not acceptable. This one is not acceptable. So when you write the algo, you have to be careful. From 1 you go to this one, and then this one come back, cannot go back to the same node here. So that's why it's not there. Okay, from 2 you can go to 1. You cannot go back to 2 lah. But the second step you can go to 3. So that's why from 2 you can go to node 3. From 3 you can go to 1, you can go to 2. From 4 you can go to 3, and the second step you can go to 1, and so on. So this one is the illustration of one hop and two hop adjacency list here. We are given one hop. We would like to use this one to form the two hop adjacency list. Now, when we do it, you have to be, let's review how to do it. First, say, for example, you must have a for loop from, you have to know what's the size of this one. N is equal to adj dot last, right? You have to know this one. And as you can see that from 1, you can get the pointer and go to the first one, right? Go to the first one. Now, once you go to the first one, say you get the 2, what should you do? You will quickly get the data and jump to here. Very similar to DFS, right? You go to here, this one is new, then you come to here. Once you find that this one is not now, then you can come to here. So from 1, you can go to 2 lah, in some way. From 2, because it's 2 steps, the first step is here. The second step it will be from 2, because you are from 2, then you can go back to 1. Oh, then this is not acceptable. This one is not acceptable. So this one cannot. So you will look at the the other one. From 1, you go to 3. You go to 3. From 3, you can come to here, right? You can go back to 1. We so-called bypass it and go to 4. Because from 3, you can go to 1. From 3, you can go to 4. So you cannot go back to 1 again, but from 3, you can go to 4. So that's why in 2 steps, from 1, you can go to 4. We get this one here. Then now we go to 2, see what we can do. From 2, you can go to 1. Fine. From 1, then you will get the pointer and then go to 2. But this is not acceptable, right? Because you go back to 2 again. So you bypass it, go to 3. Go to 3. So yes, this is okay. So from 2, you can go to 3 and so on. So in this particular algo, you will see that the first time I come here, I use an array, use a pointer. This pointer is called S, as you can see that. The next time when the second hop, the second step, we use another pointer. This is called R in my one here. So this is ADJ. This one, I think I use ADJ2 here. I change it. Okay. Okay, so we are going to use this one to form the ADJ2 because ADJ2 is for 2-hop adjacency list here. So let's see how to do it. I think the explanation is clear here. First, we have a G, and now we will use the one-step adjacency list to form a 2-hop, 2-step adjacency list. Okay, so we have a few pointers to do it. Like the input 1-hop adjacency list. Then we want to form the ADJ2 of G, right? So S is the first hop pointer to SLL node. R is the second point because you do it in 2 steps. The first step is S. The second step, the pointer is called R. Okay. Let's see this one here. We are given the ADJ. This is the one-step adjacency list. First of all, we know how big is the adjacency array here and here. So we are going to form the ADJ2, this particular array. So you create a new array. The size of it is n here. So we start to create that one. I is equal to 1 up to n here. So at the very beginning, this new the new pointer ADJ2 bracket I here should be null because it has nothing to point to, so point to null. And then the in that particular adjacency, the ADJ array here, the pointer we use there is called S2, yeah, corresponding to S1, S here. Okay, so we go back to the one step. S is equal to ADJ I, because we are talking about the I here. I is equal to 1 up to n. So we take one of them. We check it whether this pointer is pointing to null. If pointing to null, nothing to do lah. If assume that this is not null, we will get the data part of it. The data part of it will be S dot data. Once we get it, we use this one to get the pointer of that. That will be the second pointer, the second pointer. Then we look at the second pointer. we look at the data part of that. If this R is not equal to now, we get the data part of that. So when we do it, we have to check whether this data part is equal to I, because we start from I. We don't want it to go back to I. If this one is not equal to I, that means we can include it into ADJ2. So we form the new node. So we formed temp is equal to new node. The data part is called r.data, right? Because you can go to r.data. And the next, for the node, the next field is now. So this is standard free statement to create a new node here. So you see that whether S2 is equal to now. If S2 is the pointer used for the ADJ2. If this pointer is now no SLL linked to that, then the ADJ, this one will link to this temp. The new node will attach to that. If S2 here is equal to now, but S2 then, but this one is not empty here. So you have something like that. So you have to advance this one here because you have some node inside. So you have to advance this one to the next one. So S2 is not now. And then this one is equal to this one is not equal to so let me see again. S2 is not equal to now. That means S2 is this one. If it's now, then you attach to it. If this one is not equal to now, you have to attach this one to S2, the next part here. So make the SLL longer. Okay, once you do it, then you have to look at the pointer of this SL should be point to the temp. That you end the if here. Okay, so if the one here is not equal to now, you do it. If not equal to I. If it's equal to I, what do you do? Because this one is the pointer for the second R, is the pointer for the second step. If the data part is pointing to itself, so you have to bypass it. So bypass it, you have to bypass the pointer. R is equal to R dot next here. So this one will be like that. Okay, so once you have done that, then S is equal to S dot next, because we are talking about the pointer for the ADJ. Now we have finished attached to it. We'll advance this one to the next here, because here we'll see that S not equal to now. If it's equal to now, we will go to the next one. Okay, so you keep doing that. After from I equal to 1 up to n, then you will form the ADJ2 one by one, and this one become the two-hop adjacency list. So these are the pointers, and you will return this one here. So you should try to understand the meaning of each one. S will be the pointer for the ADJ. S2 will be the pointer for the ADJ2, like that, for the pointer of ADJ2. Okay, so the one step is ADJ. The two step is the ADJ2. So once you understand it, using the some adjacency list, you can try it using something simple. You can do it, but remember that if the second hop you jump to the same node here, then you have to reject it, bypass it. You have to go to the next. Okay, so I think this one is a little bit complicated. Yeah, so, and actually this one is the last tutorial problem we have. This one is slightly more advanced. Yeah, we used all our knowledge on the graph and also quite interesting here. So today we'll stop here. I will send you the link for this one. Thank you very much.